Okay, so I wanted to do just a couple more examples. The first one is explain using theorems why the function y equals sine x over x squared minus 4 is continuous on its domain. Okay. So first of all, we have a bunch of theorems that I would recommend looking over. And I'll show you the ones that are relevant to our case. So we saw that there was sine x. That is a trigonometric function. And this theorem is telling us that the following types of functions are continuous at every number in their domain. X squared minus 4 is a polynomial function. So another case where we have a function that's going to be continuous at every number in its domain. We also have here that if f and g are continuous at a and c is a constant, then the following functions are continuous at a. Here we have the quotient. Okay, the quotient function is also continuous as long as the denominator does not equal 0. So those are the types of theorems that were being referred to here. Okay, and just really quickly, so this is a trig function, so it's continuous on its domain, and its domain is R. This is a polynomial function, so it's continuous on its domain, and its domain is R. The domain of this quotient is going to be the intersection of these domains, which is R, minus any values where the denominator is 0. So the denominator cannot be equal to 2 or negative 2. So the domain of this function is negative infinity, negative 2, union 2, negative 2 to 2, union 2 to infinity. Okay, and we can see that both sine x and x squared minus 4 are continuous at all of these values, which means that the quotient is continuous at all of the values in its domain. Okay, and then this implies y is continuous. Okay, so taking this along, if we were asked to locate the discontinuities of y equals sine x over x squared minus 4, well, this is related to the previous question. We know that this function is continuous on its domain. And so what we really have to do is we have to find the domain of this function. And we just, in the previous example, we saw that the domain of this function was right here. So the only discontinuities are negative 2 and 2. These are the discontinuities. They are the values that are not in the domain of the function. But I also want to point out that not only are negative 2 and 2 not in the domain of the function, but the function is defined on both sides of negative 2 and on both sides of 2. So near both of these values, my function is defined, and that's what makes it a discontinuity. The next question I want to take a quick look at: how can we use continuity to evaluate the limit? So from the previous examples, we saw that this function is continuous at x equals 0. Okay, it's continuous at all real numbers except for negative 2 and 2. So it is continuous at x equals 0. And what does continuity mean? Well, if a function is continuous at a, it means that the limit is equal to the function's value. So we can use that here, okay, to calculate our limit. So I can go right up here and I say, hey, this function is continuous at 0. That means that this limit is equal to f of 0. And f of 0 in this case is sine of 0 over 0 squared minus 4. So that's 0 over negative 4, which is just 0. So basically, if you know that your function is continuous at the limiting value, then all you have to do is just plug that number right in. Direct substitution works in order to find our limit.